Hello everyone, I'm Sijiang Fan from National University of Defense Technology and University of Manchester. I'm so happy here to introduce our work, CNN+LSTM Accelerated Turbulent Flow Simulation with Link-wise Artificial Compressibility Method. So this is kind of a joint work between computer science and physics. Let me introduce the turbulent flow at first. Turbulent flow is everywhere in nature, but turbulent flow is very complex, so it is called one of the unsolved problem in physics. The direct way to simulate the turbulent is like in this video. At the beginning, this fluid is like the laminar, which is very steady, and then there are some fluctuating, and then gradually became the turbulent flow. But as you can see, it will take a very long time for the fluid to get the fully developed turbulent flow. So the common way to generate the turbulent flow is the synthetic eddy method, which is SCM. SCM assumes that turbulent flow is composed of two parts, the mean velocity and the fluctuating velocity. As we can see the left picture, at the left side of this picture is the time average velocity and another side is instantaneous velocity. The left side, the fluid is very steady and very simple, but the instantaneous velocity is very complex and include many eddies inside. So the SCM defines a fixed number of synthetic eddies, like the right picture. There are many eddies vect through the plane and then generate a fluctuating velocity. So what we did before is apply the SCM into the channel. So as we can see the bottom video, the left side is the inlet and the right side is the outlet. At the very beginning of the left side, the fluid is very laminar and steady, and up the area of influence, the fluid became to turbulent flow gradually. So the area is influenced by the SCM. So let's see the procedure of the SCM. After the initialization on CPU, the SCM will generate the eddies and update the velocity. Then the velocity data will be transformed to GPU. The GPU will simulate all the domain data by the link-wise artificial compressibility method. Then, after the end of the iteration, we need to move the eddy and update the velocity again by SCM. So the SCM is run on GPU or run on CPU, and the whole domain is simulated on GPU. In this picture, we can have a clear understanding the CPU and GPU runtime. We can see that the GPU is not efficiently used because the GPU must wait for CPU to generate the velocity because the eddies have passed through the plane, so we need to regenerate the eddies. But this is a very time-consuming process. And we tested the time, so the SCM takes up to 58% of the whole computational time, but this is nonsense because SCM is only an inlet boundary condition, so we must improve this. So our motivation is replace SCM with machine learning. The machine learning will be executed on GPU, and there are later things need to do on CPU. It's just some data communication and data processing. So after we replace the SCM, the timeline is changed to here. As we can see, the GPU is used very efficiently, and every iteration we only need to do some data communication between CPU and GPU. We use the machine learning, so we must need the training data. The very direct thought is to get the training data from the SCM. However, the SCM assumes that the shape of the eddy will be constant and it will advect only, only in x direction. But the fact is that the eddies will move in every direction and the eddies may be rotated, stretched, or the shape is not constant. So what we did is we extract the data from the downstream. So we get the slice at the downstream and we get these three pictures, the UX, UY, and UZ. And all the training data are from the 5 million time steps and the interval of two continuous time steps data. It is 500 time steps. And this is architecture of the CNN+LSTM. As we can see that the left side, the input is five continuous time steps of data, and the output is the data at next time. So at the very beginning, we need first first five original data in 5 time steps, and after that, the input data will get from the last predicted data. So this is a predict result for different role, which is UX, UI, and UZ. And the first column is the training data, and the second column is the predicted data after 5 time step. We can see the movement of the eddy, and the last column is the predicted data after 4 million time steps. We can still see that the eddy structure here, even after a very long time. But it is hard to measure if the result is correct or not only by this instantaneous data. So the common way to validate the result is to time average the instantaneous data. So we time average the velocity and radial stress. The time average velocity is very close to 0, which is makes sense, and the time average the radial stress is approaching the training data. Then after we validate the predicted data, then we apply the predicted data here. As we mentioned before, this area we use the SCM to generate the velocity before, but here we replace SCM with the machine learning, and the whole domain is simulated by the link-wise artificial compressibility method. Then we use the friction velocity to measure if the fluid became the fully developed turbulent flow. The friction velocity is very important quantity to to see if your fluid have become the fully developed the turbulent flow. So the red line is the friction velocity along the whole channel, and the blue one is the goal. So after the x equal to 10, we approach the ideal friction velocity. And there is a job here because we use the sponge layer here, so it makes sense. And these are the radial stress and the velocity, which is close to DNS. Here the performance. These are the gaskets is the newly released software from University of Manchester, and these 4 is linkwise with SCM on 14A16 threads by OpenMP, but we can see that after more than 16 threads used, we cannot benefit from OpenMP. So we use machine learning here. This is the time consumed by machine learning. It is 15 times faster than SCM, and the whole implementation is half the whole the whole computation time. And if we compare to the GASCANs, the our implementation is 8 times faster. And but to our best of knowledge, the most of the commercial and or the open source software cannot simulate the same scale on the same hardware. So we make these sheets so that we can have a comparison. Okay, let's do the brief conclusion. So we design a machine learning based turbulent flow generator to replace SCM and introduces into the STIG to make it work with linkwise. And then we show our work is the fastest turbulent channel flow simulation with turbulence inlet to date. Thank you for your listening. If you had any problem, please email to me. Thanks.